Well, the second piece of impact is called oblique impact, and that is when the line of impact occurs at an angle to the line of motion of one or both of the particles, and that's two-dimensional impact. All right, so what does it mean to have the line of impact be different from the line of motion? Well, here's a few examples of that. If we have this block sliding down the hill, clearly his line of motion is that this ball is coming here. The line of impact is connecting the two mass centers at the point of impact. So let's draw the mass center there and the mass center here. So this would be the line. And clearly that's different from the line of motion of the ball. It is the same as the line of motion of the block. If that's the line, then the plane goes perpendicular to that. Sometimes the line of impact is given in the problem, but you can see that this coin is moving that way, this coin is moving that way. The line connecting the two mass centers is right there, so that is the line of impact, making that the plane. And sometimes it's not given in the problem. For example, here we got this ball going this way or this disc going this way. The two mass centers are clearly drawn on the picture, but then this would be the line of impact and the plane of impact being perpendicular to that. All right, we're going to talk about the rules and how to handle those things as we go along, but that's the difference between the line and the plane and how you identified that. All right, so the line of impact connects the two mass centers. The plane of impact is perpendicular to that. There are two cases of oblique impact. However, in both cases, momentum is conserved. And on the line of impact, the coefficient of restitution is used to find the exiting velocities. On the plane of impact, the exit velocities is constant for both. It's actually the same as the approaching velocity for both particles. So that's the difference. Line of impact, you use the coefficient of restitution to find the exit velocities. And the plane of impact, the exit velocity is the same as the approaching velocity. All right, so here's a little picture. The first case that we're going to talk about in oblique impact is where a ball or something, a disc, bounces off an immovable wall. All right, so one particle is moving and the other particle is actually stationary. So let's say that this ball is coming in here, bounces off here, and bounces there. Well, if it comes in at an angle, it's going to have some component in this direction, and it's going to have some component in this direction. We define the line of impact again as the line connecting the two mass centers. So at the point of impact, this is the mass center. What's the mass center of a wall? Well, it's actually infinitely down in this direction. So what we're going to say is that it's way down here someplace. This then the line connecting them would be the line of impact, and obviously the plane of impact would be perpendicular to that, and that's going to be along the wall. So as we approach this thing, we're going to have some component in the line direction and some bounce component back that way on the line. On the plane, we're going to have this approaching velocity and then some approaching or some exit velocity along the plane. And then again, our rules, the plane is whatever this component is, it's going to be the same velocity going backwards. That's the plane, means the approaching velocity is going to be equal to the exit velocity. On the line, the approaching velocity in the line direction, the exit velocity will be determined by the coefficient of restitution. So basically it's this one, and then coefficient of restitution being less than 1 would be the approaching velocity times the coefficient of restitution is going to be the exit velocity. All right, so let's do a couple problems and we can illustrate that. All right, so here's a young lady throwing a ball, and she's throwing it in a horizontal direction. It's going to bounce on the street and then bounce this way. The coefficient of restitution is given as 0.8. She's given it a initial speed in the horizontal direction of 8 feet per second. We want to find out the maximum height that it's going to bounce to on the first bounce. All right. So, and we need the velocity just before it rebounds from the ground. All right, so let's talk about what's going on here. This is kind of a projectile motion problem. She's giving it a speed in this direction. It doesn't have any y speed but initially, but we know that as it approaches the ground, clearly it has some y speed, doesn't it? It's going to have some velocity in the y direction, we'll call it that. It's still going to have some velocity in the x direction, we'll call it that. All right, where is the line and the plane here? Well, again, the line would be connecting the mass center to down here, so this will be the line. The plane will be perpendicular to that. Okay. All right, and our first objective is to find out the the velocity of the ball just after it bounces from the ground. Well, before we can find out what it is after it bounces, we need to find out what it is before it bounces. All right, and so how can we find that Vy or V line? Well, a couple ways we can do that. We could use projectile motion, we could use energy, and we could use constant acceleration. So let's do energy. We'll say that mgh is equal to 1/2 mv squared, only in the y direction. And how high up am I? I've got the masses cancel, and I got a 32.2, and I'm up 3 feet. That's going to be equal to 1/2 v squared when I get to the bottom, and v is going to be equal to negative 13.90 feet per second. The other way we could do this is with constant acceleration, and we could say that v squared is equal to v sub 0 squared plus 2as, and the velocity here is going to be the velocity when it gets to the bottom. It doesn't have any, that's squared, it doesn't have any y speed at the start, so I'm going to say that v squared is equal to 2as, which is equal to 2 times gravity times 0.2 times the distance of 3, and I can see the velocity is equal to negative 13.9. All right, same, which is convenient, I guess. Guess I better make sure we're talking about our x's and y's. In these impact problems, the most important thing is to define the line in the plane, and sometimes x and y is appropriate as well. But all right, so now that we have our approaching velocity, let's talk about our exit velocity. Now, in impact, what we said is along the plane, v plane 2 is equal to v plane 1. So if this is the plane, we have a velocity in the x direction, and the velocity afterward is going to be the same thing. Well, what is the velocity in the x direction? We know from work with projectile motion that there's no acceleration in the x direction, so whatever it is up here, it's going to continue to have there. So I'll say that that is equal to 8I, and this is equal to 8I. So my velocity at the point of impact, v at the point of impact, v1, is equal to 8I minus 13.90j. That's my velocity at that point. All right, after impact, what is it going to be? We know that the exiting velocity is still going to be 8 in the I direction. In the line direction, we'll just draw our line equation, and that's going to be the coefficient of restitution equation, is E is equal to V line 2 over V line 1. Okay, and that's equal to 0.8. So what is my V line 2? V line 1 is equal to negative 13.9. So V line 2 is equal to 11.12 feet per second. All right, so now I've defined the vector for the exit, or excuse me, for the after the rebound right there. I know that it is 8I in this direction, and now I have in this direction 11.12 is equal to V line 2. All right, and so my total vector, if I want to use vector Cartesian coordinates, V2 is equal to 8I plus 11.12j. And again, those are convenient sometimes to use Cartesian coordinate notation on that. All right, but now I've determined what it is. The velocity of the ball is now determined. The maximum height to which it rises, now it is again projectile motion. It's going in this direction. It's got some velocity going in that direction. We can determine the height by using our constant acceleration equations again. So I'm going to say that y squared is equal to y sub 0. Beg your pardon. This is vy squared. Vy squared is equal to v sub 0 y squared minus 2as, or h here. Might as well put h. All right, what is my velocity at the peak? Well, the velocity in the y direction at the peak is going to be equal to 0, because that's what it is. And so the velocity in the y direction at the beginning would be 0 is equal to 11.12 squared minus 2, 32.2 h, and you can solve that for h is equal to 1.9, here's my paper, 1.92 feet. Okay. All right, this next problem is a oblique impact problem. It starts as a central impact problem. So here we have a cue ball being struck by a cue. It's going to go in this direction, smack the blue ball. The blue ball is going to continue on, bounce against the cushion, and come off at a different angle. All right, so this is a coefficient of restitution exploration here, and you're going to discover that the reason that you've had trouble playing pool all these years is you weren't a dynamic student yet, and you didn't really understand the coefficient of restitution all that well. But anyway, we'll see if we can make you a better pool player out of here. So this starts as a central impact problem, assuming that you strike it straight and it hits the cue ball straight on. It's going to have the momentum as it approaches the blue ball, and right before impact we're going to say that the cue ball has some momentum. After impact they're each going to have their own momentum, and so we're going to say that as a central impact problem the sum of the momentums before impact is equal to the sum of the momentums after impact. So the momentum for the cue ball is going to be its mass times velocity, and then the sum of the two mass times velocity afterward. All right, let's look at the masses for a little bit. We say that each ball has a mass of 0.4 kilograms. We see that there's a coefficient of restitution between the cue ball, and the blue ball of 0.8. So if I look at my equation, I got a mass here and a mass here and a mass there. Those are all the same. That means they all cancel out. So in this case, it's convenient, but I get the mass of the cue ball coming in of 5 is equal to the velocity of the cue ball afterward and the velocity of the blue ball afterward. All right. Well, I got one equation, two unknowns. I got to do a little bit more work. So let's use the coefficient of restitution, and we're going to say that the coefficient of restitution is equal to the two exit speeds divided by the two approaching speeds. Well, in this case, the approaching speed of the blue ball is 0. The approaching speed of the cue ball is 5. And the exit speeds are what I'm looking for. So with that, here's the rest of my equation. When I set the coefficient of restitution equal to 0.8, I end up having a two equations, two unknown situation. And you can see my arithmetic here. And I can solve the velocity of the blue ball is equal to 4.5 meters per second. So that's the velocity of the blue ball after impact. So that's VB2. All right, now we're going to bounce against the cushion, and we're going to see what the angle is of rebound. All right, so he's approaching the cushion at a 30-degree angle. According to our rules, we need to find the line in the plane. So at the point of impact, that's where he's going to bounce there, and the line of impact connects the two mass centers. So if we have a mass center here and then a mass center for the wall way back in there, we can identify this as the line. Obviously, the plane is going to be perpendicular to that, so we'll call this the plane. We have components in the line and the plane. The component of the approaching velocity is going to be the cosine in the line, so that'll be the cosine, and it'll be the sine component in the plane. And then we'll have an exit velocity down this way and an exit velocity on the line going that way. All right? All right, now let's talk about the bounce off the wall. It is an oblique impact problem. We've identified the line in the plane, and so let's just recall what we've got along the plane. We know that the approaching velocity is this 4.5 times sine of 30. The exit velocity is going to be the same thing. So whatever that is approaching, that component is going to be the same. All right, so let's look at that. 4.5 sine theta is the approaching velocity. That's going to be the exit, and I've evaluated that as negative 2.25. All right, along the line, a little bit more difficult, but not really. It's you'll have an approaching component in the line, and in this case it's going to be the cosine of that 30, so 4.5 cosine 30. The exit speed is going to be the approaching speed times the coefficient of restitution. We can discover that by plugging it into the entire equation, but we know that the exit velocity, the difference between the exit velocities and divided by the difference between the approaching velocities. For a wall, it's pretty easy because the exit velocity of the wall is 0. The approaching velocity of the wall is 0, so I just have E is equal to the ratio of the two of those two, exit velocity and the approaching velocity. I know that this one is equal to 4.5 cosine, and multiply that by 0.8, I can get the exit velocity of 2.338. All right, now I can draw a little picture of what that looks like. I know that this one is 2.338, and this one along the plane is 2.25. So the square root of the sum of the squares, and I can find out what the magnitude of this guy is 3.244. And my angle of is going to be the inverse tan of this of 2.25 over 2.338, and you can see my math here. Okay.